Hey, hi, I'm Emma. I'm Emily.
And I'm Meg, and we're going to teach you about how to solve a dynamics problem with the method of impulse momentum.
The problem we were assigned had two uniform cylinders,
Each with a weight of 14 pounds.
And a radius of 5 inches.
and they are connected by a belt as shown. If the system is released from rest when t equals 0 seconds, we were asked to determine the velocity of the center of cylinder B at t equals 3 seconds, and the tension in the portion of the belt connecting the two cylinders. The next step is to evaluate our toolbox and see which given or known equations we have. First, we know that the moment of inertia for a cylinder is I equals 1/12 mr squared. Also, we know that since the two cylinders are connected by the same belt, they have the same velocity. This means that the velocity of A is equal to the velocity of B. Next, we know from past equations that we've learned that the velocity is equal to the radius times the angular velocity, and this is true for both cylinders A and B. And rewriting this equation, we get omega A is equal to the velocity of A over the radius of A. And since we know that the velocity of A is equal to the velocity of B, we can plug that in. And then from there, we know that the velocity of B is equal to the radius of B times omega B, so we can simplify it even more. Then, for plugging in the values of the radius, we are measuring the distance from the tensile force from the belt. This gives us 10 inches for radius B and 5 inches for radius A. When simplifying, this leaves us with 2 omega B. The next step in solving this problem is to take the moment about point A. We do this by using the free body diagram made previously, taking the clockwise direction as positive. Since the angular velocity is 0, the moment about point A in circle 1 is 0. For our second circle, we multiply the force PT times the radius r and set both of these equal to the inertia times the angular velocity of A, which is found in the third circle. Then we can simplify. We know from our toolbox that I is equal to 1/12 mr squared and that omega A is equal to 2 times omega B. Simplifying even more, we get P times T is equal to the mass times the radius times omega B. And this is equation 1. After that, we find the moment about point C, which we determined to be located at the far right end of cylinder B. We do this by using the free body diagram made previously, with the clockwise direction taken as positive. Since the angular velocity is 0 for the first circle, the moment about point C in circle 1 is 0. For our second circle, we get a negative WT multiplied by the radius, and a positive PT times the diameter, which is 2r. This is equal to the third circle, which is negative I omega B plus a negative MV times the radius. When simplified, this equals negative WT plus 2PT equals negative 3/2 mr omega B. This is known as equation 2. Now that we have these two equations, we can solve for omega B. So to do this, we substitute equation 1 into equation 2. This gives us, and then simplifying, you get, and we'll call this equation 3. And we know that the velocity of B is the radius times omega B. So by plugging in equation 3 that we just found, we can get, and when simplifying, we get, and this is the answer to part A. Finally, we plug in equation 3 to equation 1, allowing us to solve for the force. And we end up with P equals 4 pounds. This is the answer to part B.